Hey, welcome back. Today I wanted to talk about how to pick up a zero location on a milling machine. I showed this numerous times during projects, but I think I never did a good explanation of some of the techniques that exist there. Apart from the good old Edgefinder, there are other options. You can use dowel pin. You can use this contraption, which you will see in hobbyists use quite a bit. This is just a ball bearing pressed onto a dowel pin. And you can use a dial test indicator. I'm skipping the Heimer 3D probe and a Renishaw 3D probe because these are the most affordable options. When we're at a milling machine and we have a workpiece clamped up in the vise, usually, especially if you're working already on a part that's finished and you want to add features, you need to know the relationship of your mill spindle to the part. And for that we use these devices. Let's set up a little demonstration and give each one a try. I'm just using a 30mm gauge block as a dummy workpiece. This is not a good gauge block, so I'm perfectly fine clamping it here in the vise. This is just one of my scrap gauge blocks. So this is held firmly in the vise, and let's say we want to touch off on this side and center our spindle of the mill over this edge, over this short edge here. Let's start with the most simple thing that we have, a dowel pin, just a round piece of steel that has been ground. If you don't have a dowel pin, you can use an end mill too and put it upside down in a collet, for example. I'm going to hold it in a regular Morse taper 2 collet in the spindle. So, old-timers, this is a lot of an old-timer technique, to be honest. Old-timers would now use either a feeler gauge or a piece of cigarette paper to touch off on the side here. And I know that the cigarette paper I use is about 40 micron in thickness. Let's double check it. Yeah, that's pretty much 40 micron. And now you just hold the paper in here and you approach the workpiece. Now we have our dragging paper here and we can zero out our DRO. Okay, just to be safe, we can repeat this maneuver and check for repeatability. I get about the same drag now, and when I look at my DRO, I'm again at 0. We're now not at our final position that we want. We need to move over the radius of the pin and the thickness of the cigarette paper. So the pin is 10016, which rounds up to 1002, and the cigarette paper is 040. 10.02 divided by 2 plus 0.04 gives us 505. We move that over on the DRO, and we should be bang on the edge of the part now. I'm choosing coordinate system 1 for our pin. And then we can compare each of the edge finding techniques to each other. So let's change to number 2, coordinate system number 2, and this will be the ball bearing edge finder, this device. One thing that I didn't do right now, I didn't check for run out on the pin. I forgot that. Usually if you did something really precise this way, you would check the run out of the pin. Instead of using a cigarette paper, you can also use a light source from behind and approach the surface you want to touch off with the pin with a flashlight from behind and watch for the light gap to disappear. So here is the ball bearing edge finder. This is a bearing with 22mm OD. I think it will help if we put a little bit of a mark on here and we let it run at 1000 RPM. An additional mark on the bearing would help so we can better see what's going on. I'm adding like 4 marks. And we're just approaching until the bearing stops spinning. There we go. Okay, let's raise it. Let's check the diameter of this bearing. Slightly undersized, but pretty precise. So we can consider this 22 millimeters. 22 divided by 2 is 11, so we move over 11 millimeters and zero out the DRO. So now we're again with the center of the spindle over the edge. Okay, that was option number 2. Let's go for option number 3, which is my preferred one most of the time. It's a regular edge finder like this. Pretty much everyone sells these. Get a half decent one. They cost like 40 bucks, but they're worth it. They repeat better than the cheapish ones. And these are basically 2 parts that are held together with a spring, and you have a sliding surface that needs to be a little bit lubricated with very light grease so that these parts can slide in relation to each other. And the way you use it, you run it at about 500 to 1000 RPM and approach your surface here, and once you make contact it starts to, at first it runs out like crazy, and the more you approach the surface, the truer it runs. At the moment you bypass the surface with the center of the spindle, it will snap to one side. Hard to explain, easy to show. So let's go. Coordinate system number 3. Today we're going to run it at 1000 RPM. So on this one, the pilot diameter down here is 10 millimeters. Spot on. So we move over 5 millimeters and call this 0 again. Okay, that was the edge finder. The nice thing about the edge finder is it's not susceptible to a runout error. You can chuck this in a drill chuck and you get the same precision as if you would chuck it in a collet, or you can even put it off center within reason in a boring head to do edge finding that way. So that's why I like these. You can throw them in pretty much every tool holding device on a milling machine and get good results. With just a pin, that's a little bit harder. Same goes for this one. This needs to be running half decent true. Now for the most fun and most versatile way of edge finding on a manual or CNC mill for that matter, a dial test indicator that's mounted to the spindle. And I like to use my shop built indicator holder here that clamps directly to the spindle. I have a set of drawings somewhere on the internet for free to download a PDF file, and this just holds it to the spindle and is adjustable. I like to set the indicator so it's horizontal, so I can read it all the time, no matter the position it's spun to. I don't need a mirror, I don't need to move my head too much around the milling machine. It's very simple that way. And also I like the stylus to be a little bit ahead of the spindle axis, like in my case maybe 10 millimeters offset. And in this direction I like it, I want it to be kind of centered to the spindle. This is not critical for precision, but it's just for convenience sake. So we have now a stylus of a dial test indicator. This reads 10 microns per division. That spins on a circle with the spindle of the mill. Okay, what can we do with this now? Not much for a beginning. We can come here and drop this down and bring our workpiece in contact with the stylus. Okay, doesn't help us much yet. We know nothing right now. Now we can spin the spindle back and forth a little bit. This helps us to find the high point. And we do this. So we spin this until we find a high spot. And then we zero out either by rotating the dial here, or what we can also do, we can just move the mill table and move the needle that way to a convenient zero up there. We zero out the DRO in this position, retract the tool or the spindle a little bit, the quill, or drop the table depending on the setup of your mill, and spin this 180 degrees. So it would be nice to be able to touch off on the surface, but we can't because we're touching off from this side. So what can we do? We can take a gauge block and hold it up against the surface we want to touch off on from the second side and extend the surface up. Then we just bring this into contact a little bit, find the high spot, and crank it to zero. At this point we are not allowed to touch the dial of the indicator anymore. You can do that on the first side, but not on the second side. Okay. Now we have an arbitrary number here. This is basically the diameter which the indicator tip spins on. We need to move over the radius of this dimension. So we take X, which is this axis, and hit the half button, which divides it by 2. Then we crank to 0. And we are there. Now we're spinning a circle right over this, over the edge. So that's the most basic way of finding one edge using a dial test indicator. Very simple. The only thing that you need is dial test indicator. You need one anyway if you do any precision machining. And something that is flat on one side. A gauge block is good, a parallel is good, a piece of ground stock is good. You can hold it up by hand. You can use a C-clamp, a small C-clamp, or a magnet. You can also use a magnet that has been surface ground on one side to extend the surface up and use that to touch off. Be sure to use a dial test indicator that is resistant against magnetism. The MAR ones that I use are labeled anti-magnetic. These are not harmed by magnets. Some are. So let's compare. Before we continue, we will compare these 4 ways of touching off on this side surface here. Okay, let's compare these methods of edge finding. First one was our dowel pin in a collet, and that's what we're going to use as a reference. We will call that 0. 2 was the bearing edge finder. 3 is the wiggly edge finder. And 4 is dial test indicator using the gauge block method. to compare these techniques, we will take coordinate system 1, which was our pin, and crank it to 0. And switch through the coordinate systems and see how much deviation we get. So pin 0. This is the ball bearing edge finder plus 15 micron. Difference to the pin location. 3 is 20 micron difference to the pin. And 4 is 20 microns difference to the pin. Let's write it down. I already wrote it down. Here we go. These three, the bearing, edge finder, classic edge finder, and dial testing here are very close together, within 5 microns. And I checked the repeatability of each one against itself at least once or twice. And the pin is off. I think we can say that these two techniques are the most reliable because they give a very good visual indication and are not susceptible to spindle runout. They're only susceptible to the roundness of the circle the bearing spin, which is usually a very small amount of error. So this one and the DTI and the spindle, I call these the most accurate ways of edge finding on a manual mill. The bearing edge finder is surprisingly close. It's basically just as good, if the runout is okay. The pin with cigarette paper was not too bad either. That's like 20 microns difference between the edge finder, DTI, and the pin. That's not too shabby. So that definitely works. Each of these techniques is absolutely viable, works perfectly fine. Why not? Go for it. Let's try the pin with a light gap with a light source from behind. So we go back to our dowel pin and we clamp it in the spindle using collet again. Here we are with a light source from behind that introduces a lot of flicker. And we bring the tool in closer. And there's the light gap gone. Let's do a repeat run. Okay. There are even more techniques. Old-timers will probably yell at me and just say, use an end mill. Okay, here's a 10 millimeter end mill. And usually the technique is you take a piece of paper and once the end mill grabs the paper, you're kind of there. I'm not the biggest fan of this technique. So the idea is to run the spindle. Okay, at some point the end mill will grab the paper and transport it through there. The only problem is now you need to know the diameter of your end mill. In this case it's a 4-fluter. It's easy because we can measure it with you know, this thing. And this is a reground end mill. This is the amount we had to move over 4.88. This is the radius of the end mill plus the 40 microns of the paper here. All of the things we did that's held in a collet match up exactly. And all of them are about 20 microns off from the methods that are not exactly critical to run out. This one is a little bit, but those two are completely independent from the run out. So I guess my collet here has a little bit of run out. Maybe check that. Okay, let's see. I expect about 10 microns of run out. Yeah, and that's what we get. Which is perfectly fine for a regular Morse taper collet. That's really not too bad. But that explains the error we get with the collet held ways. Basically, when the pin is rotating, it's 10 microns in radius bigger because it's running off center a little bit. Interesting, huh? But wait, there is more. Another application for the dial test indicator in the spindle is, of course, to center on round features on a part. So let's see how you do that reasonably quick. Again, I like the DTI to be horizontal if possible, so I can read it without a mirror behind the machine. I kinda eyeball the spindle of the mill over the part I'm going to spin with the indicator, just eyeballing it. Then we do a rough centering, a very rough centering. We bring it down, we touch off on this side and move, and we just eyeball it to be in line with the x-axis. Doesn't need to be precise. We make this 0 by moving the x-axis. And we 0 out the DRO. And we retract, then we eyeball it to 180 degrees, like this. Drop it down again. Touch off in X to 0 on the DTI again. And then we have an arbitrary number here that we want to split in half. And we hand crank this to 0, and then we're already roughly centered in the X direction. And we do the same in Y. But why? Why? And retract, spin about 180 degrees, drop down, move back, and split in half. Move Y to 0, and now we're roughly over the center of the part. Now we can fine indicate it. We bring our indicator down to make contact with the diameter we want to indicate on. And now we can spin it in contact. So this is -10, this is 0. We split the difference by moving the axis to -5, -5, -5. That's pretty good. Here we have -4, move it to -5. And then you manipulate it until you get your desired precision when you do a full spin with the indicator around the part. And this is pretty much within 10 microns now. And this did not take very long. And I prefer this 1,000 times over a Indicol indicator. I have one. I have this German-made Diacator, which is a very nice instrument, very well made. But it takes up a ton of C space, and it's not more accurate than this. It's a little bit more convenient because you can have the spindle rotate and adjust during spinning. But compared to this, this takes less C height, it's easier to set up, and in my mind quicker. So that's definitely my preferred way of centering on a round part. You can also use an edge finder, touch off here, here, center, touch off in this direction, center, and repeat in X. And you will get a very good result too. But I think a round piece is best indicated with a indicator in the spindle. Rotating on the spindle bearings around the feature you want to indicate. Okay, another application is for the DTI is of course to center onto stock. If you want to find the center point of a complete part, that's not necessarily round. And the way I like to do this, I have again indicator level slightly behind the axis of the spindle, and we drop it down a little bit so you can make contact with the part. We crank in until we make a little bit of contact here on the DTI needle, and we swing until we find the high spot. That's here, and we zero out the DTI once. Double check. Yep, still high spot. And we zero out the DRO. Swing the indicator 180 degrees, roughly. Make sure it clears the part. Drop the indicator down, crank in to 0 without touching the dial. Find the high spot. There we are, high spot, adjust to 0. And on the DRO, we take our x-axis, put in x and half. And that's our center. Now we can hand crank it to 0. Like this, and now we're in the center of the part. Now we swing it 90 degrees. And we do the same in the y direction. Move in until we make contact. Find the high spot, crank into 0. 0 out Y, retract the indicator, swing it around, crank over, drop down, make contact, find the high spot, that's here, crank to 0, and half. And we're on 0. And that's very close to the center of the part now. We can double check this by moving the indicator. So we measure on the other side, on the opposite direction. We make contact here. We zero it out, and we swing to find the high spot. Okay, it's still 0, and we retract the, oh, that's clever. So we drop it a little bit, and we make contact with the part. Doesn't need to be a precise number, we just want to make contact, and we swing it for high spot, zero out the dial, retract the tool, go over to the other side, drop down, find the high spot, and the dial should read 0, which it does. Within reason. And this shows me that we're in the X direction on the center. Okay, and sometimes it could be useful to have the indicator swing on a known diameter. You could either use a gauge ring for that, or you use the machine itself to set that diameter. And for that, you can mount a block on the table, or in this case I will use this piece here in the vise. And the idea is to drop down. We pick up this side of the block now, as I showed before with the gauge block. Hit 0, swing it around, move it over, get in our gauge block. Make contact, high spot, 0, and x half. So now we are spinning right over this edge, over this surface that's extended up. Let's say we want to set the indicator to a 20 millimeter radius flying circle. That means we move this over 10 millimeters, which you can do very accurately because we have on this machine a DRO with glass scales. On a machine without, you would use the dials or indicators and gauge blocks on the table ways. And now we can adjust the indicator very nicely until it makes contact with our surface that we use as a reference. Find our high spot, like this. I zeroed out the dial here on the indicator. That means when the needle goes to 0, this outside, the outside of the indicator ball is exactly 10 millimeters away from the center of rotation of the spindle. That's a mouthful. And we can double check that. Let's do another example. This is a 13 millimeter ring gauge. Let's set this indicator to 13 millimeter. That's 6.5 millimeter in radius. These techniques are jig bore and manual measuring machine techniques. They work on a normal milling machine too, just not as accurate. Don't expect to get micron accuracy that way on a normal milling machine. Okay, now we have this at 13 millimeters radius. Now we take this out of the vise and we take a magnet and our ring gauge. Okay, this is now a little bit hard to explain. I'm dropping down into the bore with the stylus and I'm moving in to 0. And I retract it, turn it 90 degrees, make sure it clears, and I move the table in until I get 0 here, and then I can spin the dial test indicator without crashing anything. And I get 0 here, I get 0 here, I get 0 here and here. So now that I have 0 all the way around on the dial test indicator, I know that my 13 millimeter that I picked up on the gauge block by moving the axis over 13 millimeters is correct. And why would you set your indicator to a certain diameter? For example, to measure a radius. If you had a half blended radius and you wanted to measure the actual diameter of it, which you can't because it's partial diameter, you can use a dial test indicator that way to measure it. That's all jig bore techniques. If you want to know more, about these techniques, go and buy Moore's book, Foundations of Mechanical Accuracy, and Holes, Contours, and Surfaces. Those two books explain these techniques very well. So that's setting the indicator to a certain diameter without having a ring gauge. I just used the machine's travel to set this diameter, and I confirmed it using this ring gauge. If I have a ring gauge, of course I can do it different. or I can use a set of gauge blocks and do it that way. There are many ways. But I like this technique because it's reasonably simple and doesn't need much equipment. So I hope you enjoyed this brief conundrum of edge finding techniques, indicator, edge finder, stuff like that. Thank you all for watching. Thanks for the ongoing support, really. I really appreciate it. And thank you all for watching. I'll be back.